to start, Stefan, give his second talk.
Thank you very much. So I will introduce today the so-called tube algebra. Now the word may sound a bit strange, and actually it won't become exactly clear why it's called like that. The word goes back to a construction of Ocneanu. And the point is that I will not present this original approach, and therefore the word tube won't become clear anyway. Now we will put ourselves at the start in this very general setting where you look at any quasi-regular inclusion, and I will remind you in a minute, of two unfactors. And we will add an irreducibility assumption. Now, what is quasi-regularity? This means that S is spanned by finite index D subbimodules. Densely spanned, yeah? Finite index D subbimodules. And as I said, we have two examples to keep in mind. One example to really fix your mind and somehow understand all the concepts is really of ordinary cross products. So a countable group acting on a two-one factor, and then to have the irreducibility assumptions. So it's for an outer action, an action by outer automorphisms of a two-one factor. But then, that's not the example for which we will deduce new results. The example that we are really after is, of course, the SE inclusion, the symmetric enveloping inclusion of a subfactor. But to understand some of the basic constructions that I will be doing, it's sometimes easier to think for a while of this example, yeah, of a cross product. Okay, now what is very good is that although this sounds as a very analytic data, an inclusion of two unfactors, usually to describe it, it's really a combination of algebra and analysis. Because of the irreducibility and the quasi-regularity, there is already right from the start quite some algebraic input, because there is a canonical dense star subalgebra, namely this linear span of the finite index D bimodules. Canonical dense star subalgebra. Say curly S, script S, given as not, densely spanned, I should stress here then. And you can quite explicitly write it, namely, it consists exactly of those elements in the algebra, so that if I look at the D bimodule generated by that element, that this one is finite index. And this is quite a natural thing to do, because in example 1, so the cross product example, so in example 1, this is nothing else than the linear span of T and UG. And indeed, it's not very hard to see that if you multiply elements of that form, that you again have an element of that form. I mean, you do span a dense star subalgebra of the cross product. Now, why am I saying this? Because what we will now do, so the theorem that in this generality was proven by Sorin, Dima Shlyakhtenko, and myself at the end of 2015. But I must immediately add that Neshveyev and Yamashita proved this for SE inclusions. before is the following. I will construct a star algebra. We construct a star algebra, namely the cube algebra A, such that this star algebra, its ordinary Hilbert space representations of this single star algebra will be in one-to-one correspondence with S bimodules, and I will remind that later, S bimodules say H, such that as a T bimodule, okay, that's a reminder of yesterday. When we have a quasi-regular inclusion, we will fix, and I will explain that again later, we will fix a preferred family of T bimodules, and we will be looking at all S bimodules that as a T bimodule are a sum of such. Yeah? And then you will see that this cube algebra will also depend on this choice of T bimodules, and representations of this one single star algebra are in one-to-one correspondence with such Hilbert S bimodules. And so let me first explain this construction in this complete generality of quasi-regular inclusions, because then the construction of the cube algebra is extremely natural to write. And then I will specify in the second part of the talk today what happens in the specific case of a tensor category. Because in the second part I will really somehow forget about one factors, and right away define this star algebra purely in terms of a tensor category. No reference anymore to ambient to one factors. Okay, but I think it's worthwhile to see the construction of this star algebra in this full generality. And somehow what you should be thinking of is that in a way we are trying to recover from the inclusion of T in S the group algebra of gamma. That's roughly what we are doing. And of course, in that ad hoc situation, you can do it because you can recover the group from the inclusion, and then you can recover the group algebra from the inclusion. And then we all know that indeed the group algebra, representations of the group algebra is the same as representations of the group, is the same as bimodules of such and such a type. So there the language, there is nothing new and nothing surprising. Okay, so what is the construction of the cube algebra? So the construction of A. Well, there is a further initial data. So the data is not only this inclusion and a category, a tensor category of finite index T bimodules. Category of finite index T bimodules. C. So if you wish, you could take just those that are generated by S, yeah, that appear in S and then all their products. That would be a canonical choice. Okay, with that I will construct first a vector space. And then put a product on that vector space. As a vector space, so that's now really my C gamma as a vector space, if you wish. As a vector space, I would take A to be a direct sum of the following. I take all kinds of irreducibles in C. And now there will come strange notation that I have to explain. Not self-explanatory at all. Okay, what is this? It will be a space of intertwiners, but interpreted in the right way. So this is, by definition, all, and now comes the word, finite rank intertwiners from, and again I have the wrong convention, but well, which I think is the right one. I will argue in a minute. From the following, let me write it in a Hilbert space way. So S is a 2-1 factor, L2 of S is a nice t bimodule. I fixed a category of finite index t bimodules. Each irreducible is realized by a concrete t bimodule that I write like this, Hi, Hj. Now, of course, t in S is very much infinite index. So this is not a finite index t bimodule. Neither is this one. So I don't want to look at a space of all intertwiners. That would be algebraically very hard to handle. I only want those that only live on finitely many a sub t bimodule of finite index here, and a sub t bimodule of finite index there. Now, then you may wonder, okay, there are different types of restrictions what one could impose. You could say, okay, I only want a finite index t bimodule as a whole support for the morphism. Now, of course, since this one has finite index, whether I restrict here or in a whole, it doesn't matter. I mean, that's the same kind of restriction, okay? And then there is another good thing. Given an irreducible t bimodule, by our irreducibility assumptions for the inclusion, it can only appear with finite multiplicity in S. That follows automatically from the entire construction. If you look at the cross product case, for instance, every t bimodule appears with multiplicity 1. And that's in general for any quasi-regular inclusion of 2-1 factors with irreducibility. A given irreducible t bimodule can appear at most finitely many times in S. So therefore, any type of finite rank assumption that you may want to impose will give you the same thing, okay? Whether it's only finitely many irreducibles that appear, or really, okay. So let me introduce a notation to clarify this. So the notation is the following. That's original. So yesterday it was just the light that switched off, and now there is a new presentation that comes up. It's very fancy. Okay. So notation. Given a subset of irreducible bimodules, finite, denote EF, the projection onto the span of all those in F, if I may write so. Because L2 of S is a t bimodule, which is indeed a sum of finite index t bimodules by assumption. So if I specify a given subset of irreducibles, I can project exactly on the sum of those irreducibles that are in the set F. Yeah? So that's a nice projection EF. And then I can write the finite rank assumption better than V from L2 of S over T Hj to Hi L2 of S is finite rank. Given only if there is such an F that covers it on both sides. So V is the same as V E F tensor 1, so only those play, and it's the same as only reaching those. Okay, is that concept more or less clear? Or okay, and now I can put a product. So I will now define the product in the following way. So I take, and now you will maybe start to agree that conventions to write the order of the morphisms are not that stupid, because I will multiply something with a j on the right with something with a j on the left. So what is the product of two such intertwiners? Well, the product in the algebra that I'm about to define, v dot w, is the following. At first I write v tensor 1, 1 tensor w. This is now an intertwiner that starts from twice L2 of s at hk, and it ends up in hi and then twice L2 of s. And the kind of thing that I apply to land again in such a thing is the multiplication morphism. And it's adjoint. Hilbert space adjoint. So here M is the multiplication map. Here M is multiplication. And what I will write makes no sense. Because we all know that in infinite index inclusions, as we are dealing with here, this is not at all continuous and well defined. So only once it's covered by one of these finite index or finite rank projections, it's really defined. Otherwise, these things are not continuous. You don't extend it to the entire Hilbert space and so on. But if I decide to only take a finite index sub-bimodule here or a finite index sub-bimodule there, then it's a well-defined bounded operator. And you see that I'm actually only applying it when there is implicitly such a bound, because the v's and the w's are covered by these, yeah? Okay? And then you can see that also the product is still covered, is still finite rank, so there is a nice multiplication thing. So I think that this is a very transparent formula, especially if you will compare it to the formula that appears in the definition of the product for the tube algebra, for a tensor category. So in the tensor category setting, yeah, it's slightly stranger what appears, but this one is, I think, very transparent. Okay, so there is also an adjoint, because we want the star algebra, and there will be a canonical functional, a trace in the extremal situation, in the unimodular situation. Okay, so let's define the adjoint as well. The adjoint.
Question from an outsider.
Yes.
It's clear that this product is associative.
Yes, because that would be the associativity of the product in S.
Oh.
So the associativity of the product in S would be, on the formal level, I take the tensor product of 3, whether I first multiply there and then the rest, or I first multiply in the first 2 and then the rest. And that's the only formula that would come up. Because you would only have to interchange M tensor 1 with M and 1 tensor M. I mean, that's, yeah. So it is associative. Okay.
And you only multiply things when they match.
Yes. So maybe before then, okay, to clarify this, maybe before putting the adjoint, let me put clearly that there are canonical idempotents attached to every I, so that indeed, actually, we have canonical idempotents. I for every irreducible. it's really graded in that way if you wish. And they are orthogonal, these idempotents, yeah? So we have canonical and orthogonal idempotents in the algebra, and if I take this kind of component of the algebra, then, or corner, then these are exactly these spaces. And therefore you see indeed, I only multiply when they match, otherwise the product is 0, yeah? Because then I'm multiplying two orthogonal projections. Okay, so then the adjoint. I can also say what is pi, by the way. So define the following inclusion morphism. So the trivial bimodule sits inside S always, and then pi formally, then pi would be nothing else than the following morphism, namely 1 tensor delta, delta star tensor 1, and this is, if you look carefully, indeed an intertwiner from L2 of S tensor I to, because I go from S to the identity to the trivial, and then I come back from the trivial to S, and this is indeed a morphism in my defining space. And then the fact that multiplication with T is doing nothing, you can indeed see that it plays the role of pi would act as a left unit on this one, and j would act as on the right as a unit in these ones. Yeah? So these are the canonical idempotents that live in the star algebra. And then remains the adjoint. Adjoint. Well, define formally the duality T from the trivial T bimodule to this T bimodule. If T in S would be finite index, then we know that taking the bimodule and its adjoint, there is a canonical way to embed the trivial T bimodule inside, but now it's not. I mean, it's very much infinite index. Formally, we would like to define this as the dual of the product composed with delta, but only after covering things make sense, yeah? Again. Now, so that's the input, and now I can say what is the adjoint. So given V as an intertwiner from Sj to Is, we write V cross, and you will see immediately why I write a cross and not a star. Is given by because of course a morphism has an adjoint. So that's the thing you have to keep in mind. V in particular is a linear map. I mean, it's between Hilbert spaces. It's a linear map from this Hilbert space to this Hilbert space. So it has an adjoint from this Hilbert space to that Hilbert space. That's not the adjoint in the algebra. It would not even be an element of my algebra. Yeah? But I can modify this with the duality morphism T. And this one is the adjoint in my star algebra. And so now you can make the computations, and even exact formulas for the purpose of today are maybe not so important, But the proposition is that we have a nice star algebra. You have a question.
Yeah, it looks like you have there are
Three.
you have three maps, and it looks like there should be two maps.
What do you mean by 2 and 3
Right,
maps?
so, okay, V pound, either V, whatever, has, on the other side, you have three maps, and it looks like it should be a map between the tensor product of two spaces.
But it is.
So,
This one should start. No, but T starts from the trivial T bimodule.
the trivial one, okay, good.
So
Okay,
T
good,
starts
good.
from the trivial bimodule, which is absorbed in.
So those are different
yeah,
tensor products, one of those is a tensor product over T, and the other one is a tensor product
Everything is
over-
tensor product
it's
over
everything
T.
over T, okay,
Every tensor product sign will be over T.
gotcha.
Every formula is in, say, T bimodule maps and tensor products.
Excellent.
Other questions? Okay, so what's the bottom line? The bottom line is that starting from any reducible quasi-regular inclusion of 2 factors, you build this type of star algebra. I didn't write you the canonical functional you have on it. This canonical functional on it will be exactly a trace when we are in a unimodular situation. Like yesterday, it means that the T bimodules appearing in S have equal left and right dimension. If they have different left and right dimension, the proportion between the two will show up in the modular theory of the corresponding functional. There is a nice Hilbert space completion of A. It has an accompanying von Neumann algebra that will be used tomorrow. I will talk again about it to define the two Betty numbers, because then this von Neumann algebra will really play the role of the group von Neumann algebra. Okay, so what's the theorem? Maybe now I can state it again and okay.
Stefan,
Yes.
in the case of a cross product, so this should boil down to very simple things, right?
Yes,
Because
but not exactly to the group algebra. Do you want me to do the exercise? Maybe that's it's worthwhile.
well, I was thinking that in general you have no idempotent in a group
No,
thing, so
No, so that's indeed a good exercise to clarify things. So I think we can erase the exact formulas. Once you see that this is the vector space that we are putting together, then, well, you can believe that we can invent a number of formulas to define a product. So let's do the exercise in the, okay, very good. In the case of a cross-product inclusion.
Is it also fair to say what you've defined as a sort of new category structure on C?
A new category structure on C.
You would think of this algebra as just being kind of packaged.
It is an algebra in the category, if you wish.
Maybe I'll say more than.
You can think of it as a new category, but you can also think of a category as an algebra. It's interchangeable. But yeah, and the old category does sit inside this one. You add more objects. But see, he's only done irreducibles here instead of all objects in the category.
But that
Oh,
wouldn't
right,
really
okay,
matter.
okay.
That wouldn't, yeah.
You can.
So what if we start with so then there is a very obvious choice of category. It just the C is the group gamma. Well, I mean, the irreducible objects are one-dimensional and are labeled by the group elements, and the product is just a product in the group. So let's not do more than that. And then, in the same way, what is this curly S? This is the sum of all these irreducible objects as a bimodular. Yeah. Okay, so now you can do the exercise and you can see what are the possible ways to to go from so
It's the algebraic dress on.
yes, because this is the linear span really. So it's of course the
So that's like the group algebra.
so it's the span of T u G. But we somehow we encoded the category as a category of T bimodules, and then the T bimodule given by the group element G is this one, so as a bimodule, it's really the sum of all the group elements. And then you see that what you get here is so functions on G will be part of the algebra, and that will be the idempotence. So the function that's 1 in a group element G will be the idempotent that corresponds to G. And now here you can see it would be the linear span of all K1 and K2 of okay, now what happens? I mean, all objects are one-dimensional, so this could be 0 if the two group elements are different. And it would be the complex numbers, it would be the multiples of this group element if they agree. So if K1, or maybe rather say G, equals K2 H K1 inverse. Or well, the two equal, so now you have to make the right identifications, but to cut a long story short, what you get as A would be the algebraic tensor product. You take all finitely supported functions on gamma, and you take the cross product with gamma, algebraic, and acting with the adjoint action, so by conjugation. Conjugation is maybe better, I don't know. Conjugation on gamma. So gamma is acting by conjugation on itself, and you can make a cross product star algebra, purely algebraically, and now you see that for every group element we have an idempotent living here, and in particular I have a favorite idempotent, namely the one with the neutral element. That's my favorite idempotent, and if I take the corner with that idempotent, you see the neutral element is invariant under conjugacy, so that's the group algebra is really only a corner of this algebra. The algebra itself is larger. But for studying the group, it's not very much more interesting to look at this slightly weird algebra and not only looking at this. But for the category point of view, it will be absolutely crucial to not only look at this. And I will go deeper into that when I come to the categorical point of view. Is it somehow clarifying the notations? Or?
We get not really the group, but okay. All the inner automorphism in some sense.
Yes,
But
and
I think there is a moron.
yes, and let me say a few more words because this is a good occasion, I think, to do that. In the last lecture, I will present quite a few examples that come from compact quantum groups in the sense of Voronovich, Q deformations of compact Lie groups. And if you start to do examples coming from there, somehow this example is also a compact quantum group algebra, namely for the dual of gamma, that's the compact quantum group behind. And then we will actually use a theorem by Nezhveyev and Yamashita identifying this kind of star algebra, also with this kind of cross product in the quantum world that people may recognize as the Drinfeld double construction for compact quantum groups or whatever, Hopf algebras in general, and so on. That's one occasion where it shows up, and another, that's a thing that I did together with Yuki Arano. There are examples of these tensor categories and such quasi-regular inclusions coming from totally disconnected groups. So if you do this for there are constructions involving totally disconnected groups, where again you have a nice subalgebra, namely the locally constant functions. You can make an algebraic cross product. You don't have the neutral element anymore that's equally nicely invariant, and a lot of the properties of the category, and that was quite nice to illustrate, depend on the dynamics, how the totally disconnected group is acting by conjugation on itself. Yeah. So, okay, now I'm drifting away from the topic.
I'm fairly sure that this funny algebraic cross product appears in one of the early papers by Bohm and Kohn on the Bohm-Kohn conjecture, actually the one where they construct the Chern character in homology.
I see.
They need exactly that cross product.
That's funny.
Because they need to localize in conjugacy classes.
Mm-hmm.
So
Okay.
that's how they do it.
Okay. So the theorem that I wanted to restate now is the following. In a slightly more precise way, although I won't give you all the formulas. So the theorem that we proved with Sorin and Dima is that there is a one-to-one, so we fix D in S and C are fixed. And then from an S bimodule, a Hilbert S bimodule H, such that as a C bimodule, it's a sum of C. Things in C is really the same as non-degenerate right A modules, right Hilbert A modules. Okay, and I won't write you how exactly to do it, but let me give you one glimpse, namely what would be this Hilbert space. I mean, A has idempotence pi, so if I have an A module K, a Hilbert A module K, K pi should be a concrete Hilbert space somehow that I can recover from here. And that's nothing else than the Hilbert space of all intertwiners as T bimodules. Yeah? So this is an irreducible T bimodule because it comes with. This is an irreducible T bimodule, and I look at all morphisms from HI to this T bimodule, and since it's irreducible, this has an obvious Hilbert space structure, and that's the link. And now you have to invent the formulas. Yeah. A final remark on this very general setup is that as a star algebra, this A is extremely well behaved with respect to representation theory in the same way as C gamma. So why is a representation of C gamma so nicely the same as a unitary representation of the group gamma? The reason is that even if I just have a pre-Hilbert space, and just a star homomorphism of C gamma to that pre-Hilbert space as pre-Hilbert space operators, already I know that everything is bounded and that there is this kind of uniform norm that bounds everything, and you have a nice, full C-star algebra that you can define, universal C-star algebra, and so on. This algebra A has the same properties, but it's more involved to prove it. So any star homomorphism to any pre-Hilbert space will automatically be by bounded operators. There is a kind of L1 norm that must bound everything. So therefore, there is a good universal C-star algebra around that encodes this representation theory. And therefore, also, if you want to go into things like property T and so on, you can also really use this universal C-star algebra and phrase it there, like with group C-star algebras. So it's a very well-behaved object. Okay, now I will actually just erase everything except the left-hand side. And I will do in the specific case of the SE inclusion, but even without referring to the SE inclusion, exactly the same construction, but now purely for categories. So now the same construction, and that's really Ocneanus in the case when there are finitely many irreducible objects, but the generalization is straightforward. Yeah? It's the same formulas. So let me call it Ocneanus tube algebra. Of a rigid C-star tensor category. And think of a category of finite index bimodules over a 2-1 factor, or of a representation category of a compact group, if you prefer. So what is it as a vector space? As a vector space, it's the sum over all irreducibles I and j as before. And then I take again a sum over all irreducibles. And I look at intertwiners from alpha j to I alpha. And again, there will be idempotents. So there will be idempotents. And if I so the joint will be this vector space. Yeah? Now, I will immediately give you the product of this algebra, yeah? But let me first say, what you recover if I take the favorite idempotent corresponding to the trivial representation, the trivial object. If I take the trivial object in the category, you see that what you find is a sum over all irreducibles. But then I have morphisms from alpha to alpha, that's just complex numbers. So this means that I have a basis for the vector space indexed by the irreducibles. And it will be an algebra. So you see what it must be. It must be the fusion algebra. I'm tempting to write this in this way, the fusion algebra. I don't know, actually, is this what people would usually write?
K naught C.
K naught. Like this?
Capital.
Capital. Oh, that's hard for me. That's very hard for me.
Usually K naught is over Z anyway. So
Yeah.
Oh.
It's complexification.
Okay. K naught would be over Z, not over C.
Yeah.
Yeah, you should complexify.
Oh, so then I will keep my
She
decision.
came back to the very sentence when you take it.
Of course, for me, if I'm thinking of the case of a discrete group where the irreducibles are just gamma, and this is C gamma, yeah, the complex group algebra. So why am I already stressing this? Because it will give you a slightly better intuition for the formula for the product. But also think, for instance, of the simplest case where you have the representation theory of SU2. So if you take representation theory of SU2, we all know that the fusion algebra is just polynomials in one variable. Now I was saying that our algebra have a nice representation theoretic behavior, and in particular that they have a universal enveloping C-star algebra, a universal C-star norm. Now you will say that's very much not true for the polynomial algebra. And indeed, the whole miracle is that the good representation theory is not to just represent the fusion algebra, but only those that extend to Hilbert space representations of the entire A, not just the corner. These are the good representations. And then you get a universal C-star norm. And I will come back to that. Yeah? Even to just say what is positivity, you can now get a better glimpse of it. Maybe I can also write that in a formula. This is the right framework to define positivity. Because, let me write as a kind of butade, not all positive functionals on the fusion ring are positive. So the good condition is that they should remain positive on the entire A, and that means that we want the following. I still have to define my adjoint and my product. So it might be tempting, thinking of polynomials, to say that a functional is positive if omega VV star is positive for all V's in the polynomial algebra, then I get way too many positive functionals. The good positivity condition is that I have to allow the V from the entire P epsilon A, and then again doing V cross, I get this kind of thing, and that's the good positivity condition to define representations and so on, and positive definite functions. Because functionals here on is of course just maps functions on the set of irreducibles. Which are the positive definite ones? Well, the one that give you this positivity condition, not the ones that just give you a positive functional on the fusion algebra. Yeah? Okay. So now the product, and then the adjoint I let you invent out of that formula. So I can only take a product if in the middle it matches with the same idempotent. And now I would like to do the same thing as before. I would like to write this morphism. Now this one in the middle comes from and I would like to contract to certain gammas and gammas at the same side yeah? And that one can do by indeed putting a sum. So we get the sum over all irreducibles gamma. And what will be the component? I take the sum over all x. One tensor x star, x tensor 1. And what is x running through is an orthonormal basis of isometries from gamma to alpha beta. So I do decompose with the sum of isometries. I completely decompose my alpha tensor beta as a sum of gammas. And then you see, because of the presence of both x star and x, it doesn't depend on the choice of the orthonormal basis. And this is the product in the star algebra. Okay? And here it's because I cheated a bit when I was doing the thing with the quasi-regular inclusion and the group case. Here, if you fill in the group case, you really get on the nose this conjugation cross product that I was putting forward. Okay. So again, we have a nice star algebra. And the theorem that Schweyer and Yamashita proved is that indeed bimodules for the SE inclusion is the same as just star representations of this star algebra. No, that's not what they. What am I saying actually? That's what you proved.
Yeah, I was.
You should have said. So you see, there are too many. But now I wanted to make the whole picture, and now I realized that I was saying stupid things. So now we have the whole picture. Take an SE inclusion. And we have the cube algebra. And so bimodules here, well, not all, but we have seen it now a few times, is the same thing as representations, just star representations of this cube algebra, and this is really what yesterday I got it right, what Gordon Jones did. And then there is what Yamashita Nefeyev did. And that is the Drinfeld center. We take the int category. And we take a so-called unitary half-braiding. It's not a concept I will use any further in the lectures, but I will in a minute nevertheless give you the definition to show you that there is yet another picture that is purely in categorical terms, and then you can actually, of course, pass back and forth because the category need not come from bimodules somewhere. So for any C-star tensor category, there is a way to go back and forth between representations of this abstract star algebra and then the so-called Drinfeld center of the int category. So let me now explain you in even more categorical terms what is a unitary representation of a C-star tensor category. Well, what is int C? Let me cut a long story short and just say allow infinite direct sums. And an infinite direct sum of objects, you can turn it into, you can think of it as a Hilbert space in a way. At least the spaces of intertwiners, you can consider them in a nice way. You can tensor them because it will be again a direct sum of things in the category, so that's not a problem. So you can build a new, not rigid, but you can build a new C-star tensor category called the int category. So what is a unitary half-braiding? It's really somehow, in notation-wise, the closest you can get to a unitary representation. Because what is a unitary representation of a group? It's a Hilbert space and a map with unitary operators. Well, here it's a bit of the same. It consists of a carrier Hilbert space, namely an int object, a direct sum, possibly infinite direct sum of objects in the category C, and for all alpha, you will see how little I know about category theory, because I really feel a bit on shaky grounds now. I'm sure you should write this in the kind of right natural functor from here to there, and I'm just unable to do that. So I will really write a unitary operator, namely for all alpha in C, a unitary intertwiner, a unitary morphism, sigma alpha, from, now I should get things right, otherwise mix up, from alpha x to x alpha, okay, and what are the natural conditions that this thing should satisfy? Well, the naturality only in the alpha part, or a half braiding, not a braiding, such that. So naturality means that if I compose with a morphism to beta, I should get sigma beta. V is now a morphism that starts in alpha and ends in beta. And then it should be multiplicative. So multiplicativity is now very nice. And that's it. And what Neshveyev-Yamashita proved in the case of SE inclusions is that there is a one-to-one correspondence between these special bimodules for the SE inclusion and such unitary half braidings in terms of the category. And then you can complete the picture and go, if you would prefer to stay in terms of tensor categories, you only look at the bottom line. You take any tensor category, you define the algebra, the star algebra A over there, star representations of that algebra. It's one and the same thing as unitary half braidings. Now, you may say, why is it useful to have both pictures? So it's really relevant to have both pictures because there is the notion of a tensor product of representations. So, how to take tensor product of representations? Well, this is very much okay in the half braiding and the bimodule picture. Because we all know how to take, I mean, here it's really taking tensor product over T for the bimodule, so it's a very nice thing to write. Here, the same. The carrier Hilbert space you will take, well, Hilbert space. The carrier object will be the tensor product in the int category, no problem, and you have a very natural formula to write a tensor product of representations. Here, the formula gets extremely messy and not very natural to write it in terms of the tube algebra. So if you're more interested in the monoidal part, you see that you have two favorite pictures. But now, what we will do tomorrow is what about cohomology and homology? Well, this is more or less only okay using resolutions for A, because we will have the whole homological algebra machinery. Once you can talk about homology, cohomology for a star algebra, everything is possible. And I wouldn't like to try to do that in either of these two pictures. So it's really because you can pass between all of them that the whole machine starts to work. Yeah? Okay, so now we have the players on the scene, so I can now say more concretely what I will do in the remaining lectures. Tomorrow I will start by introducing from scratch homology, cohomology, L2 Betty numbers for groups, and then define them for tensor categories using this algebra A. And then in the last lecture I will give examples, mainly coming from compact quantum groups, and I will particularly focus on temporally Leuven algebra, of course. Okay, thank you very much.
Thank you. Any questions or comments?
Just one small thing, at the very beginning, was C actually closed under tensor product?
Well, to make the construction, it doesn't matter. But you would typically take it. Actually, in full generality, even here, you could define the algebra for any choice of objects, any set of objects. I choose representatives of all irreducibles, but you need not. You can give exactly the same definitions for any choice of objects there. And then as long as you would make the choice so that every reducible appears in at least one of these objects, then you would get a strongly Morita equivalent star algebra. So therefore it doesn't matter really what you do.
Is C also semi-simple?
Yes, I mean rigid C star tensor category, every good property you may want.
Every object is a direct sum. Really.
Yes, yes, yes.
So in your picture of the group acting on itself by conjugation,
Yes.
that comes up in Fried-Hopkins-Tellman's picture.
In, sorry?
Fried-Hopkins-Tellman, they describe the Vlinder ring, which is what you have.
Okay.
So in the, say the compact group case,
Yes.
so they use the symbol that you don't like. So it's the, so you take the K theory of that.
Yeah, but then
Right.
that's really K theory then, yeah?
Yeah.
That I like.
Really take the K. So, but in order to incorporate the twist, so the cutoff, they take twisted equivariant K theory. So the twisted equivariant K theory of that algebra you wrote down
Okay.
is the Vlinder ring. And that had been noticed already by Lustig for the finite group.
Okay, I will take a look at that. Thank you. So that's Hopkins, you say?
Fried-Hopkins-Tellman.
Okay, wonderful.
Any more comments or questions? Okay, so we'll carry on again tomorrow. Tomorrow is the afternoon.